plate boundaries. In order to understand convergence, we've got to talk a little bit about the crust. Now, our crust, or our lithosphere, is broken up into different sections called plates. Now, our plates can either be made up of oceanic crust or continental crust. Please know the difference between the two of them, because when those two types of crust interact with each other, they're either going to slide side by side, they're going to pull apart from each other, or in this case, they're going to crash together. So when we talk about convergent plate boundaries, okay, we're dealing with three different types: ocean to continent, ocean to ocean, or continent to continent. So let's take a look at some of the geologic features. Okay, we're going to start off with ocean to continent. Your crust is destroyed here. The surface, some of the plates, are going to be destroyed at convergent plate boundaries, specifically ocean to continent. They're going to be destroyed through a process called subduction, which we'll touch base on in a second. You also get mountain ranges at these types of plate boundaries. Some of those mountains are volcanic. You tend to get very strong earthquakes. And you tend to get offshore trenches. So let's take a look at what this looks like. So our ocean to continent convergence. Our convection cells are going to take our oceanic crust on the left, and they're going to cause the continental crust on the right to collide with each other. Because of the density differences, your oceanic crust is going to move underneath your continental crust. It's going to plunge into the earth. That's what we call subduction. During the subduction process, there's a tremendous amount of friction, so you're going to get some very strong earthquakes. As that plate gets deeper and deeper into the planet, it gets hotter. Eventually, it gets hot enough where the plate starts to melt. So the leading edge of that plate melts. The magma is going to be forced to the surface. You tend to get a mountain range that runs parallel with the coastline. Some of those mountain peaks tend to be volcanic. Where those two plates interact with each other, that's what we call a trench. Trenches tend to be some of the deepest points on the planet. Let's take a look at where some of these features can be found. First off, in North America, you have a very small plate called the Juan de Fuca plate. That's subducting underneath North America. You are going to get your subduction, big earthquakes, mountains, trenches, and some of those mountains tend to be quite active in terms of volcanism. So you're going to get what's called the Cascade Mountain Range down the west coast of the U.S. You get the same features at the Cocos Plate, where it's subducting underneath North America and the Caribbean Plate, and you get the exact same features here with the Nazca Plate. What's important about the Nazca Plate subducting underneath South America is that you have the Peru-Chile Trench there. That's the location of the biggest earthquake ever recorded back in 1960, 9.5 on the Richter scale. You also have a very big mountain range down the west coast of South America called the Andes Mountains. Well, this map is on page 5 in your reference table, so please make sure you know how to read it. You have a little bit of trouble, come down to the key at the bottom. That symbol there tells you exactly what a convergent plate boundary is going to look like. Now, in North America here, we have the Cascade Mountains. It's one of the more prominent mountain ranges we have. It's a very volcanic mountain range. And like I mentioned before, Mount St. Helens, Mount Hood, Mount Rainier, just some of the many volcanic peaks that are active in this volcanic mountain range. The second type of convergent plate boundary is ocean to ocean. And again, you get the exact same features. Crust is destroyed here through the process of subduction. You're going to get mountain ranges. Some of those mountain ranges can be volcanic. You're going to get some very strong earthquakes. Okay, and you're going to get some trenches. Well, what's the difference between ocean to continent and ocean to ocean if you get the same features? Let me show you. Because you have the same type of crust colliding with each other, one of the crustal plates has to move underneath the other. And the one that's going to move underneath the other is going to be the one that's going to be a little bit more dense. You notice that they're both crustal plates, are both oceanic, but the plate on the right has a little bit of continent attached to it. So what's going to happen here is that the more dense oceanic crust is going to subduct underneath the oceanic crust that has some continent attached to it. Now, what makes this difference is the only difference you have is the fact that your mountain range, your volcanoes specifically, are in the water and not along the coastline. You get subduction, you get the big earthquakes, you get the trench system, you get the mountains and volcanoes. Instead of being on land, now they're in the water. Let me show you where some of these locations can be. The Aleutian Islands are an ocean-to-ocean convergence, highly volcanic. Your Japanese islands, ocean-to-ocean convergence, highly volcanic. You have your Mariana Islands and the Philippine Islands, okay, both highly volcanic due to the ocean-to-ocean convergence. And you also have your Indonesian islands due to your ocean-to-ocean convergence, and also your Tonga Islands, same exact thing. So all of your features are going to be similar, except now what's going to happen is your volcanic mountains are in the water that produce volcanic island arc system. That's essentially the big difference between ocean to continent and ocean to ocean. Now you notice many of the locations around the Pacific Ocean that border the Pacific Ocean are going to be highly volcanic, big earthquakes because of massive subduction zones. Okay, we also have a couple locations in the Atlantic Ocean. We have a small subduction zone with the Caribbean plate. We also have a very small subduction zone down here with the little sandwich plate. Again, all of these features are going to have strong earthquakes, subduction, mountains, volcanoes, and you're always going to have a trench system as well. So please be aware of the features that can be found with ocean to continent and ocean to ocean. Okay, so I just alluded to the Pacific Ocean. The perimeter around the Pacific Ocean is what we call the Ring of Fire, or the Pacific Ring of Fire. Very simply because some of the world's largest volcanoes exist around the perimeter of the Pacific Ocean, and some of the world's most violent earthquakes have occurred around the perimeter of the Pacific Ocean. Because of the fact we have such violent subduction, violent earthquakes, and big volcanoes, it's coined the Ring of Fire. The third type of convergent plate boundary is continent to continent. In this case, you legitimately have continental crust crashing with continental crust. So what's going to happen? Again, crust is destroyed in this location. Subduction is going to occur, but it's not very deep, so you get very little to no melting at all. So your mountains that are produced, okay, are not going to be volcanic, and you tend to get, again, very strong earthquakes. Let's take a look at the best location on the planet for this. Because your continents are going to crash together, you get what's called crustal uplift. The crustal plates tend to get forced upward, so you tend to get some of the tallest mountains in the world. So here's your continent-to-continent convergent plate boundary, and the best location for this is going to be India crashing into Asia. And the mountain range that's produced in this case is going to be the Himalayan mountains. Okay, the best location can be right there, the Indian-Australian plate crashing up to the Eurasian plate. Again, you notice that you have continent-to-continent convergence, very big mountain range produced due to that massive crustal uplift. You also have another location here with the Arabian plate crashing up into the Eurasian plate. You have a small mountain range called the Zagros Mountains at that location. Okay. And here's India and the Himalayas. Beautiful shot of the Himalayan mountain range. So that's it for now. Good luck, and we'll talk to you soon. Today we're going to be talking about divergent plate boundaries. So this is one of three types of plate boundaries on the planet. We have convergent, we have transform. This one we're going to be talking about divergent. Now divergent just means pulling apart or moving away from each other. Now there's two different ways in which you can get divergence on the planet. You can either have oceanic divergence called oceanic ridges, or you can have continental divergence called continental rifting. Now notice I have two different words that mean the same thing. There are some synonyms: ridge, rift, rise, and divergent. They all mean the same thing: plates moving away from each other. Now there are some geologic features. Okay, convergent plate boundaries, crust is destroyed. Here is the baby factory for crust. This is where crust is created. Underwater mountain ranges tend to be created here. You do tend to get some volcanoes and some earthquakes. Not nearly as violent as your subduction zones, but you still get a few of them. Now this is a regions diagram that shows your plates separating. Classic diagram of a divergent plate boundary. The crack right in the middle gets filled up with magma. And then an artist's rendition of what the mid-Atlantic ridge might look like, which is the mid-ocean ridge in the Atlantic Ocean, with the big crack right down the middle of the Atlantic, separating North America from Europe, and then South America from Africa. Okay, so if we first start off with your mid-ocean ridges, these are basically found underwater. So your plates are pulling apart underwater in this case. Where the crack in the ground is going to be found, that's where your rift is going to be filled with magma, and that's really where your youngest rock is going to be found. Okay, this is the longest continuous mountain range on the planet. Okay, it almost acts like seams on a baseball as they continually go around the planet. And because majority of these can be found underwater, indicates that the plates underwater are getting bigger. Scientists call this seafloor spreading. Now, if you look at page 5 in your reference table, there's a continuous mountain range called the Mid-Ocean Ridge. It just has different names in different locations. In the Atlantic, it's called the Mid-Atlantic Ridge. In the Pacific, it's called the East Pacific Ridge. In the Indian Ocean, it's got a couple names: Mid-Indian Ridge, Southwest Indian Ridge, and the Southeast Indian Ridge. In case you get a little bit confused, go down to the bottom of your map. Notice the key, the little zigzag pattern, and the arrows moving apart. That's your divergent boundary. So scientists had to come up with a couple pieces of evidence to support seafloor spreading. The first one's going to be the age of the seafloor rock. Because magma is going to be found right at the ridge, that's where the crack in the ground is going to be. Okay, that's going to be the location where your youngest rock is going to be found. Brand new rock is found right at the rift, right where the crack in the ground is going to be found. So youngest rock is going to be at the ridge, and as you get farther and farther away from the ridge, it tends to get older and older and older. So very important to know the age of rock in relation to the ridge. You also have something called the reversal of magnetic polarity. Our Earth has an invisible magnetic field around it. We know that because when you walk outside with a compass, your compass needle points north. Okay, this is all caused by the Earth rotating and the fact that we have a liquid iron and nickel core. For the most part, we have a liquid outer core and a solid inner core, but that core is going to rotate with the Earth. It's going to create that magnetic field. Well, we know that magma comes to the surface, it's going to contain magnetic minerals. So what scientists have been able to find out is that the minerals in the rock, when they solidify into rock, will lock in the polarity at the time of formation. So most of our rock we have on the planet is going to have dominant magnetic north polarity with the minerals. But scientists have found certain areas on the bottom of the ocean floor that have rock that have dominant south polarity, which gives an indication that at one time our magnetic field has flip-flopped. It has turned upside down, where instead of having dominant magnetic north, at times we have dominant magnetic south. So this has provided evidence, the rock itself has provided evidence of possible magnetic reversals with our poles, and it provides some sort of proof that we've had some flipping of our magnetic fields. Now, over the past 330 million years, scientists believe we've had about 400 of these reversals. And it's all about looking at the polarity within the rock itself. So what you want to look for is you want to look for the pattern on both sides of the ridge. You notice right at the mid-ocean ridge, you have normal magnetic field. And as you go east or as you go west, it alternates different zones. So it's going to go normal, reverse, normal, reverse, normal in both directions from the ridge. And that's going to indicate that as our seafloor spreads, the new magma coming up is going to lock in the polarity at that time. Sometimes it's normal, sometimes it's reversed. Here you can see not only the age of the rock, newest rock is at the Mid-Atlantic Ridge, oldest rock is furthest away, but you also see the different zones. You see that you're starting out with a normal polarity, and in both cases you're going to go side by side. On either side of the ridge, it's going to go an alternating pattern. And you notice that they're mirror images of each other. They're the exact same pattern because your ridge tends to diverge at roughly the same rate. Continental rifting. Well, there's two locations where the continents are splitting. One is Iceland, and one is the East African Rift. These are two locations at the surface where divergence is actually taking place. And you can see here's a picture of Iceland. You see part of Iceland is part of North American plate traveling west. Part of Iceland is on the Eurasian plate traveling east. There's a big crack right in the middle. So every time the Mid-Atlantic Ridge splits, Iceland tends to get a little bit bigger, tends to get bigger earthquakes and volcanic eruptions. And here's the East African rift. You can see the Arabian Peninsula is moving in a northeast direction away from Africa, and you have a very big section there. See the arrows moving away from each other, a big chunk of the eastern part of Africa that's moving to the east. So very important to understand where those two divergent zones are going to take place on the continents. And again, page 5 in your reference table, you have Iceland in the middle of the Atlantic Ocean, and you also have the East African Rift Zone. Okay, that's it for now. We'll talk to you soon. Thanks so much. The most prominent transformed plate boundary we have on the planet is right here in the United States, right in California. Okay, that's going to be the San Andreas Fault. A transformed plate boundary just means when two plates slide side by side next to each other, traveling in opposite directions. Your San Andreas Fault is going to be the boundary between the North American plate traveling south and the Pacific plate traveling north. Now, you tend to get extremely strong earthquakes at this type of plate boundary because you have tremendous friction between the two plates grinding against each other, traveling in opposite directions. So your convection cells are going to cause one plate to travel north and the other plate to travel south in this case, with the San Andreas Fault in this case right in the middle. And here's an actual photograph of the San Andreas Fault. Okay, the big crack right through the middle of the picture with the North American plate and Pacific plate on either side. So you can take a look at your page 5 tectonic plates chart in your reference table, and you can see that the San Andreas Fault is going to be the most prominent transformed plate boundary, but it's not the only one. You also have some subsequent ones in the southwest Indian Ridge. You have a small one off to the south. You also have a few along the Scotia Plate, and you also have one to the south of the Tasman hotspot. So they are prominent on this map, with the San Andreas Fault being the most important. Just in case you get a little bit mixed up, okay, you have your key at the bottom of your map. That leads us to hotspots. Now, hotspots are a funny phenomenon because you tend to get volcanoes in the middle of a plate compared to along a plate boundary. So a plate is going to move over top of a magma pocket or a pool of magma underneath the surface. The magma is going to get forced upward through the crust and a volcano forms. So you tend to have a very active volcano over top of the magma pocket. What happens is the plate moves and the active volcano moves with it. So that volcano becomes inactive as the plate moves off the magma pocket. What happens here is that a new volcano will pop up behind the inactive one now. And this happens over and over and over again. You tend to get a string of volcanoes with the only one that's active is the one that's over top of the magma pocket. That's essentially what a hotspot is. So some of the geologic features tend to get very strong earthquakes due to the fact that you get the quantity of magma traveling up to the surface. You also tend to get some very vibrant lava flows as well. The Hawaiian hotspot tends to be the most widely studied. And you notice that Kauai is about 5 million years old, Oahu is 3 million, Molokai is 1.8 million, Maui is about 1.3 million, and Hawaii is the youngest. Kauai is the oldest and it's the smallest. Hawaii is the largest and it's the youngest. So just by looking at the age of the islands and the size of the islands, you can tell that Hawaii is on the hotspot and the Pacific plate is traveling in a north or northwest direction. That's a classic example of how a hotspot is actually going to be documented with your extinct volcanoes on the plate. So all those volcanoes are extinct with the exception of the active island of Hawaii. Now Hawaii is not the only hotspot. You have a bunch of them. You have the Tasman, the Easter Island, the Galapagos, the Yellowstone, the Bouvet, the Canary Island, the Iceland, and the St. Helena hotspot. So you notice a lot of those hotspots are found away from plate boundaries, which means that the magma pocket is feeding active volcanoes as the plate moves over top of it. In case you get a little bit mixed up, you have your little symbol right down there in the bottom right-hand corner of what a mantle hotspot would look like. So, over the course of this chapter, we've been able to find out that your earthquakes and your volcanoes tend to be found in the same regions. We usually find our earthquakes and volcanoes along crustal boundaries. So when you take a look at your tectonic plates chart, most of what you're looking at here is going to be your subduction zones, your divergent boundaries. That's where the majority of your earthquakes and volcanoes are going to be found. With that being said, thank you very much, and we'll talk to you soon. Bye-bye.